So welcome to the last talk on this conference day. I'm going to talk about Spring Boot and Project Leyden. So who here knows about Spring Boot? Very good. Who uses Spring Boot? Very good too. Who knows about Project Leyden? You're going to learn something. And who uses Project Leyden, preferably in production? Okay, great. Okay, about me. Normally this, I'm not that stretched, but I had to improvise with the slides because the Wi-Fi doesn't work. So you see how I look here. My name is Moritz Halbritter. I work in the Spring engineering team. I primarily work on Spring Boot and on start.spring.io. So the Josh Long's favorite place on the internet. So what I did work on in Spring Boot, I was hired for the GraalVM native image support. So I worked for the Spring Boot 3 release, primarily on GraalVM native image stuff. But I also did other features, for example, like the observability story with OpenTelemetry and Micrometer, Docker Compose and test container support. We worked on virtual threads, SSL hot reload, CDS, which is the predecessor of AOT cache, which we're going to talk about later. Also SBOM, so the software security side of things, structured logging, and in the Spring Boot 4 release, I worked primarily on the JSpecify nullability stuff. But I'm also doing a lot of performance work, and this is what this talk is about. Okay, so to motivate, what's the problem? What's the problem with our application, actually? This application started in like 10 and a half seconds. Who think that's acceptable? Is it good? Would you like to see that? No, okay. What's the problem when it starts that slow? So the problem is the CPU time you spend on startup, it costs you money. Either because it occupies your own server, which you have in your basement, or you pay your cloud provider money and they bill on your CPU time. And the other problem is that long startup time limits your scalability, right? But why do we want scalability? I mean, I just swapped one motivation for another motivation. So why do we want scalability? One thing is to handle traffic spikes. So you have your application running and it's all good. And then you're featured on whatever, Slashdot, it's not a thing anymore, but Hacker News or whatever. And then people click on your link and then the site is like really, really slow because you can't handle traffic spikes. You still run on one instance, this instance is saturated, and then stuff gets really slow. And responsiveness drops. Like users hate slow websites. You know how that is. Like not working Wi-Fi is better than slow Wi-Fi. Right? So to ensure responsiveness, we need to scale. That's why we want to have scalability. You also, if you don't have scalability, you also run into problems with rapid recovery. Think about your Kubernetes cluster and one pod goes down. And if the pod takes like 30 seconds to start up, that's a problem because now the crash pod is restarting, but it takes like 30 seconds. So you only have a window of 30 seconds where the other pod should not crash. If that crashes, you're essentially completely down. And it also saves money and energy if you can do scaling, because think about it, you only use the resources you need, and when you need more, you scale up and you pay more, but if you need less, you scale down and you pay less. And if you take that to an extreme, that's essentially scale to zero, right? There is no instance running, no money spent on anything, and then a request comes in, and then you scale up. And this only works if you can start fast, because no customer is going to wait for like 10 seconds to handle this request. But if you can start in, I don't know, 100 milliseconds, 300 milliseconds, that's totally acceptable. No instance is running when no traffic is there. The first request comes in, you start the application, let it handle the instance, and everyone is happy, and you save essentially money and energy. So this is why we want to have fast startup. The goals for this talk are, I want you to understand how Project Leyden boosts Java startup and performance. I want to demonstrate how to use the Leyden-related stuff, which are available with JDK 25 and Spring Boot. And we are also going to learn some techniques you can apply today, like with a real-time, with a Java 25, what you can download from the just Java website. And I give you some techniques that you can apply that like today. Okay. First, talk about Project Leyden. What is Project Leyden? Project Leyden is named after this Leyden jar here, and this is a thing from 1800 or whatever, and it can store charges of electricity. And the idea of Project Leyden is it's a prototype, and prototypes in Java work that way. They essentially fork the JDK, and then they work on that stuff, and sometimes they merge it back. And with Project Leyden, they worked on a lot of stuff which has already been merged back. Okay, and the idea of Project Leyden is the problem that Java is slow to start, right? This is the problem they want to fix. And what they are going to do is they improve the startup time and actually the warm-up time. So the startup time is until your application can handle the first request, and the warm-up time is when your application is at peak capacity, at peak performance. So when it can handle the most amount of requests, essentially. And they do this by shifting computation earlier or later in time. What does that mean? The general idea is you compile your stuff to bytecode with a Java C compiler and using Maven or Gradle or whatever build tool you use. Then you create the cache file while you're still in build time on your machine, on your CI server, whatever. Then you copy this cache file into production, and then you use this cache file. And this cache file then makes your stuff fast starter and reach peak performance soon. That's the general idea. That's what they say by shifting computations earlier. So why would you only compile bytecode to native code in production when you can do this while doing build time, for example? Java is a static type language. Okay, so we have a type system, thankfully, which catches errors before when we compile stuff. But Java has a lot of dynamic features. For example, like you can do reflection. You can create classes out of thin air at runtime. You can create proxies. You can do serialization and other dynamic stuff. So there's a trade-off involved here. To essentially to know what the application is doing, you have to observe it dynamically. So if you run it, the JVM is looking at your code, which is currently running, and does profiling. And with this profiling, this feeds into the JIT compiler, and then this JIT compiler creates from your Java bytecode native machine code, which can then be given to your CPU to execute, and which is really, really fast. So this is the major thing why Java is really fast while you're compiling to bytecode, because there is the magic of the just-in-time compiler. And for that, you need dynamic observation. And for that, we need training runs. What's the idea of a training run? The idea is essentially you exercise the startup and the warm-up code path while you're observing that stuff. So you discover ahead of time what you otherwise only find out at runtime. And this is to do that you can do this in your build time, and we see later why. So what is this training run? A training run, the best training run actually, is to observe the application in production. But in bigger companies and heavily regulated industries, there's always some security guy who's nagging you and breathing down your neck and tell you can't extract production, you can't extract data from production. And there are very good reasons for that. So usually the first option here, it's not realistically achievable, but that would be the best thing, to just observe the thing in production, extract the profiling data somehow from production, and then use it. The next best thing is to simulate production. And for that, you write a small driver program, for example, an integration test, which simulates production while you're still in the build time, and do the same traffic patterns your production would do. So the virtual machine can learn the same patterns like it would be in production, and then we can use them. And those runs at build time. And why do they work? They work for exactly the same reason why they work in production. We don't observe that stuff in production, but we observe it in our training run using production-like data, and then we should get the same effect, right? And the analysis is driven by what the program actually does. So we need to somehow exercise the code path. We can't just take a static look at the bytecode and find out what it does, because Java is too dynamic for that. And that's why we need a training run. So now back to Project Leyden. JDK 10 introduced class data sharing. This is the CDS I talked about, and this is the predecessor. This is the forerunner for ahead of time class loading and linking, which has been delivered in 24. And this is a thing of Project Leyden, which has been taken from Project Leyden into mainline Java. So you can download that right now. And this is ahead of time class loading and linking. I'm going to talk about that in detail. JDK 24, it's called the ahead of time class loading and linking. the command line flag is AOT cache. That's why I'm always titling this stuff AOT cache. So we first do the training run. And for this, we start our application, stock standard Java, and this time Java 24. We tell the JVM, go in the record mode, and we point it to the green file, and then we start our application. And this time here we were using a class path, but you can also use like minus jar, and then point it to a jar file. And then you do your training run. So you essentially run your integration test against it, or you open it up in a browser and click around a little bit, and then you exit the application. And on exit, it writes the green file. And then we transform the green file in the orange file. And this is the AOT mode create. This takes the green file where Java has essentially recorded which classes has been loaded all the time. And then it transforms this green file into the orange file. And the orange file, this contains like the loaded classes, which are now cached. And cached loaded classes are a lot faster to load than to load them without the cache. And then you copy the orange file into production. And then you point Java to this orange file. You can throw away the green file. And you give it the orange file, and then it starts up faster. That's the idea. Okay, what's in the orange file? So if a JVM loads a class, it has to do a lot of stuff. First, it needs to find the class. And to find the class is not that easy because there's usually a hierarchy of class loaders. So you have to ask the first class loader, do you know the class? No. Okay. And you ask the parent, do you know that one? No. And so forth and so forth. And then one class loader will go into answer, yes, I know where the class is. And cool, yeah, give me the byte array for that. And then you need to verify the class, you need to link the class, you need to resolve the class, and it all takes time. And this is what the cache does. It has resolved in the training run here. Here. It resolved it already, put it in the cache, and the cache contains already parsed class metadata, loaded and linked classes, and resolved constant pools. And this stuff can just be memory mapped into the process space and then be used, which is much, much faster than to load all the classes by hand. That's the cache file and the idea and the fast startup. And then JDK 25 came along, and you may have wondered, why do we need the green file if I throw it away anyway? Like, why are there 3 steps? I want the orange file. Why is there no one command to get the orange file? The JDK team thought the same. They did the JEP 514 ahead of time command line ergonomics. This essentially gets rid of the green file. Now it looks like this. First thing, it creates the orange file. And then the next time, you copy the orange file to production, and then you use the orange file. Okay? Only 2 commands to remember. One is AOT cache output, which writes the orange file, and this reads the orange file. And then it's fast. But they also delivered other stuff from Project Leyden, this time to Java 25, which is called ahead of time method profiling. What's now in the cache? Parsed class metadata, loaded and linked classes, resolved constant pools, so the stuff which is from JDK 24 in the cache. But now there are method execution profiles. Method execution profiles is essentially here, if you run your application, the JVM observes what methods are called, how many times they are called, with which parameters they are called, and these are the method profiles. And this is normally fed into the JIT compiler so that this thing can produce highly optimized code. But they only store the method execution profiles in the cache. So you can essentially skip the profiling phase because you already did it in the training run. This needs a real training run. So if you want to have method execution profiles, you need to think about the training run. And Java 26 is also from Project Leyden. They improved the ahead of time object caching with any GC. And before that, it only worked for the serial and the parallel and the G1. And after that, it also works with Shenandoah and with ZGZ if you're using. Okay, so it now has it now supports all the GCs. Okay. Now let's talk about AOT cache with Spring Boot. No more JEPs. Get it real here. First, we start our pet clinic. This is the stock standard pet clinic we always use for benchmarking. This is no AOT cache enabled, and we start in 3 seconds. Okay, this is our baseline. This is done on my machine, and it may differ on your machine, but just to get like feel for the numbers, we started in 3 seconds. Okay. Let's talk about AOT cache requirements. There are some. First, the same JVM must be used. Okay, the JVM which you use for your training run and the JVM you use in production must be the same. same vendor down to the same point release. Otherwise the cache file can't be loaded. It doesn't explode and crash and burn. It just ignores the cache file and it starts up slow. Okay. The class path. It must be specified as a list of jars. You can't have directories, no wildcards, and no nested jars on the class path. And this is interesting because if you take a look at this thing which comes out of Maven build or Gradle build, usually it's a big fat jar file. And there are nested jars inside it, which is like bad. Because this thing here says we can't have nested jars, so we have to do something with our Spring Boot application. And the deployment class path must be a superset of the training one, which is like complicated words for you can append stuff at the end of the class path, but you can't change the class path like in the front or something. So you can put more jars on it, but no less, and you can't reorder them. And if you copy the files around, like the jar files and the cache file, always make sure that the timestamps are preserved, because the JVM has a fast path to invalidation, and this takes a look at the timestamps of your jar files, and if you alter them, the JVM thinks the cache file doesn't match the jar file and just throws the cache file away. And then it starts slow. Okay. To fix the nested jar problem, we need to extract your Spring Boot application. And I'm not sure if you know that, but every Spring Boot application has a hidden main class, which you can enable with -d jar mode tools, and then you can point it to your application. This here is your application file, and you say extract and give it a destination directory, and then it extracts itself. So every Spring Boot fat jar knows how to extract itself. Okay, there's a bit of code contributed by our Gradle and Maven plugin that does this magic. And if you take a look at what is in the extracted tree, is another application jar file, but this time this is not the same as that one. It's only the same name. But this one is much smaller because it only contains your code and your resources and nothing else. And then it has extracted all the libraries which are in this fat jar file under the lib folder, and now it's a flat list. And now we specify this as a list of jar files. We have no directories, no wildcards, and no nested jars on the class file, and now AOT cache is happy. That's the reason why we need to extract it. Okay. The funny thing is, you can even extract it even if you don't care about AOT cache at all. Just extract it and it will start faster, because to implement this nested jar approach, the JVM doesn't know about nested jars. It only can load class files inside jars, but if you put a jar file inside a jar file, the JVM doesn't know about that and it can't handle it. So Spring Boot has a custom class loader, which knows how to essentially deal with jars inside jars, and this has a bit of a performance penalty. And here you can see we are starting the extracted version of the jar file without AOT cache, and you shave off 500 milliseconds. Okay, just by getting rid of this jar in jar stuff, you shave off 500 milliseconds. Okay, small little trick. You can try it yourself. Okay, now we want to talk about the AOT cache. We need to think about a training run. There are two ways to do a training run. The first one is the hard one: get production data or write a production-like integration test. The other one is what I call the poor man's training run, and this is this thing here. And this essentially only caches class loading, but not the warm-up thing. So you improve startup speed, but you don't improve warm-up speed with this thing here. And there is a parameter which is called spring.context.exit on refresh, which is built into the Spring framework, and you can run your application with it. And what it does is, it starts your application. Spring Framework instantiates all the non-lazy singletons. It invokes the after property set lifecycle method, and then it just exits the JVM. It does not invoke lifecycle start, it does not publish any events, and it does not run your application. The idea is capture the class loading of the most important classes and then exit. Okay? It doesn't connect to databases, it doesn't open WebSocket, web server ports, or whatever. It just caches so it just observes the class loading until a certain point, and then it just exits. Okay? And this is super easy to do because it's only one parameter and you don't need to think about production stuff. Okay, now let's try. First, we create the AOT cache. So we create here the orange file. We pass in the poor man's training run parameter, and we point it to our application jar. And this is the important bit. Use the extracted one. Otherwise, it will start slow. Okay, you don't get any warnings. You just get like it starts slow. Use the extracted one, then it's fast. Now let's take a look at how big is the orange file, how big is the cache file, and this thing here is 53 megabytes because it contains like, it's a binary file, it contains like the loaded classes and method execution profiles and all the other stuff. Okay, and now you copy that in production and then you start it. And for that, you just point it to the orange file and you use the extracted version again, okay? And then let's see what happens. Okay, you see that one? We're down from 2.6 seconds down to 0.8 seconds by using AOT cache. This is the price you pay for loading classes all the time and for extracting jars inside jars and stuff like that. I use time to first request in this benchmark here. Time to first request is not the startup time. Time to first request is the time until the web server answers to the first request which I send it. This is normally longer. It's always longer than the startup time. And with that, you can't hide latencies by doing everything lazy, because this uses all the machinery. So we are down from essentially 3 seconds to a startup time of 958 seconds, which is a speed up factor of like 3.1x. Okay, think about that. By using the Pullman's training run, AOT cache, copy the AOT cache over, and started with the AOT cache, your application now starts 3 times faster. Isn't that cool? I mean, and this is one of the I don't think there is any Java flag on the JVM which gives you a performance factor of 3.1x, which is like crazy. The RSS, this is the measurement of how much memory it uses. It's a little bit slower. It's a little bit less. So you save a little bit of memory here. And the user and kernel time, this is an interesting metric because this is usually what your cloud provider builds you on, and this is what burns the energy and destroys the atmosphere. You're down from 13 seconds to like 6 seconds, which is a startup factor of 2x. Okay, so this is the energy used by starting up. Okay, but that's not the end of the story. This is only AOT cache, and there is much more. If you read our documentation, you maybe came about Spring AOT. And now we have AOT cache and we have Spring AOT, and why do everyone name their crap AOT? So what's the difference? The AOT cache is a JVM feature. Okay, this is developed via Project Leyden, now in Java 24, 25, 26. And this has been developed by the OpenJDK team. And it's a feature of the JVM. So it works for everything which runs on the JVM, any framework, your application without any framework, your homegrown framework which you use inside your company, whatever. It supersedes CDS, okay? So you can forget about CDS, the new thing is AOT cache. And then there is Spring AOT. And Spring AOT is something the Spring team built. And we originally built that for GraalVM native image support. But it turns out that you can also use it on the JVM to speed up the process when running on the JVM. And how this works is it generates code ahead of time. So when you're building your stuff or the bean arrangement, so it looks what inside your Spring application context is. And instead of reflectively generating that when you're starting up, it essentially writes out code, which we then compile, which then starts up faster. And it also does other stuff. For example, like it pre-generates Spring data repositories, which normally use proxies, and then they use like compiled code, which is faster. Okay, we're going to enable that. With that here is spring.aot.enable, that's the parameter. And then it starts up in 0.6 seconds. Okay, so we shaved off another like 200 milliseconds. Okay, so we started with 3 seconds and we were down to 7.5 milliseconds, which is a startup factor of 4x. Okay, by enabling Spring AOT. Spring AOT has the drawback that you can't change your bean arrangement after you have built your application. So for example, add profile or other properties which enable or disable beans don't work anymore. But usually can work around that. And if you don't need the 200 milliseconds, just don't use it. The RSS goes down a bit too. Here, we're down to 400 megs. And the user and kernel time goes down a bit too. It was a factor of 2. Now it's a factor of 2.6. Okay. Let's talk about ahead of method time profiling. So the stuff I talked about, this only speeds up class loading because you've done the poor man's training run. Okay, you've not observed that stuff with production-like data. It only caches class loading, which gives you a startup boost, but not a warm-up boost. JEV 5.1.5 is the idea that you put method profiling data inside the cache, so that the JVM, when it starts up, it doesn't need to observe before it can compile, but it essentially can start compiling instantly. Okay, ways to do training runs. I hinted at that. There are 2 ways, hard way and easy way. Easy way is stop the application before content refresh or the poor man's training run. Easy setup can be done by building the image, improves the startup time by caching initial class loading, but it does not improve the warm-up time because it does not collect profile information. Okay, because the hot code path which are normally running in production, they are not being run inside your poor man's training run. And this is the hard part: run integration test or mirror production traffic, or run it in production and then get the cache file from production. This exercises many or all hot code paths actually used in production. It improves the startup time. It improves also the warm-up time, but it can't be easily done. There is no magic Spring Framework parameter which does that for you. This is the hard part of Project Leyden, so you need to think and do this yourself. And this is a more involved setup. Okay. This is a nice flowchart to show you what you should be using or what you can use. Okay. Do I care about startup speed? No. Okay, then you can leave. Yeah, have a nice day. Do you care about performance? No. Then you can use the poor man's training run. And is this now enough startup speed? If it's good, cool, done, nice. Check the sprint and get a celebration. If it's not, you should maybe look into GraalVM native image. GraalVM native image is a technology which delivers more crazy performance. There are more trade-offs involved, but like starting this in 600 milliseconds, GraalVM will only laugh about that because GraalVM starts in 50 to 100 milliseconds or so. It's really extreme performance because it compiles all the stuff natively. Okay, so if you want to have performance, which is a nice warm-up, then you need to do a real training run. And this small bubble here is maybe playing the problem down a bit, so you have to think about how to do that. And now, do you have enough performance? Yes, have a nice day. And if not, look into native image. Okay, so this gives you maybe an idea what you can use and what you should use. Oh yes, yeah, you're right. Yeah, there is an image. There is an arrow missing from here to here. You may have a nice day if you use native image. Native image has some trade-offs, but all of those are workaroundable, and the native image team is working heavily to get all the Java libraries supported. But you're right, there is a thingy missing from here to here. There may be some hurdles, but they are all workaroundable, and if you've done that, you get really great performance. Okay. Okay. Let's talk about requests per second, because you can't see warm-up when you only look at bar charts. This is the plain application, and this is restricted to one CPU because otherwise you won't see the curve at all, because I tried it on my 32-core workstation, and you don't see any graph because it's instantly hot, because it uses like 31 CPUs to compile all the stuff. So I restricted it to one CPU, and what it does is it takes like around 15 seconds to reach peak performance. Okay, this is here the elapsed time of the benchmark, and this is how much requests per second it can handle. And here it reaches like 15 after 15 seconds it reaches peak performance. If we enable the IoT cache with the profiling information, what I would expect is that the other curve, it starts up here sooner, so it moves essentially to the left. And this is what we see here. So the time spent on collecting profiling data is essentially shorted. The JIT kicks in sooner, and then you reach peak performance sooner. And there's a weird dip, which is, I don't know, I measured it multiple times. The dip is always there. I have no idea what this is. Maybe it's de-optimizing or whatever. And here, then it reaches peak performance. Okay. All of this, what I've shown you, like gone from 3 seconds to 0.6 seconds, is already possible using Java 25. There is no preview flags, other weird stuff, self-compiled JDKs. Everything is usable right now using Java 25 or Java 26. So there's no excuse to not do that stuff. Okay, but Project Leyden isn't done. Project Leyden is an ongoing project, and they want to still deliver stuff. This is a JEP draft. It has not been targeted to any JDK, but this is ahead of time compilation. And what it does is, why only profile data, or why only profile in your training run when you can also compile it in the training run, right? Why should you let the JIT compile it in production like every time when you also can compile it at build time? And this is the idea to do that. Okay, what's in the cache? Class metadata loaded and linked classes, resolved consent pools, method execution profiles, and now pre-compiled native machine code. Okay, so while the training run is running, the JIT is compiling stuff, and the compiled code is not thrown away. It's stored inside the cache file, and if you copy it into production, it's loaded and it's used. Okay, but this needs a training run. Let's try that one. So this Java here, you see, this is the Leyden Java. Okay, this is a pre-compiled, this is a self-compiled Java from the Leyden repository. And now it starts up in 0.45 seconds. Okay, so we've gone down from 3 seconds to 600 milliseconds, which is a startup factor of 5x. Okay, this is the stuff you can expect from future JDK upgrades once they essentially merge Project Leyden into mainline. To get that, you need to clone the Leyden repository yourself. You need to run the JDK build, and then you get Leyden JDK, a Leyden-enabled JDK, and then you can get those benchmark numbers. Okay, so this is not suitable for production, but this is like a glimpse in the future what is there to come. The RSS, like, not really changed here, but the user and kernel time is like crazy. Because all the time, all the time you spend on while starting up, you already did in build time. You profiled all the data, you compiled all the data, you linked and loaded all the classes, and now we're down from like 13 seconds of CPU time burned and built down to 2 seconds of CPU time, essentially. Built and burned, which is a factor of 7x, which is like nice. Request per seconds to see how this compiled code behaves in production. So what would you expect what the new graph is doing? Any idea? Yeah, right. Vertically up, instantly hot. It shifts more to the left. Let's see what it does. Yeah, that's almost what we see. So the orange curve starts much sooner, but as you can see here, it never reaches peak performance of the other thing. Okay, so the pre-compiled machine code, which is stored in the cache, is apparently not as optimal as the JIT-generated machine code at runtime. Okay, there are 2 open bugs for that, because the JDK team thinks this is a bug, and they should investigate and fix that, and I guess they will fix that. But there's an important thing behind that. There is always a balance of performance and portability in Project Leyden. So if you have a very powerful workstation with all the AVX instruction sets, and you build the cache file with this specific machine architecture, and then you deploy it onto production to your potato where you put like metal plates in it, should it still work? Should it just fail? What should it do? Should it throw away the compiled code and recompile again? So because this is now compiled machine code, which is very, very targeted to your actual machine you're using. So if your production server is different from your developer machine, there's always a balance to strike here. And portability is a priority, so they defensively compile, I guess, to not the most optimal performance, which you can see here. This is why the yellow thingy never reaches the blue one. And I'm very curious to see how they solve those two bugs here. This also applies to other parts of the system, like heap sizes, garbage collectors, and stuff like that. Because a JVM, it doesn't always use like G1. If you give it a small enough heap, or if you give it only one CPU, it defaults to serial GZ, for example. And if you run your training run on your developer machine with a very small heap or only one CPU, then the machine code also has the machine code, which is generated by the JIT, often interacts with the GC. So if you switch then the GC at production time, for example, to G1, the machine code doesn't match the GC anymore, and then you have to throw it away. So it's a very interesting research topic here. The JDK team also wants to extend the AOT capabilities to user-defined class loaders. This was the reason why we had to extract the Spring Boot jar file, because it can't handle customized class loaders, which we install to load jars inside jars. Okay, so the training run is currently focused on the 3 built-in class loaders, system extension, and bootloaders. The bootloader is not the Spring bootloader, it's the Java bootloader. Okay, that's a different thingy. And the class is loaded by them. User class loaders would benefit from the same concept, but there are a lot of challenges to get there. And if the OpenJDK team says there are a lot of challenges to get there, I totally trust them that there are really a lot of challenges. So we'll see if this will be delivered in the future, but it would be absolutely awesome, because then you ignore the extract part, essentially. The Spring team is also working on AOT improvements. For example, we have modular Spring AOT in the pipeline. So for now, Spring AOT freezes your bean arrangement, and it also generates classes, which would normally generate it at runtime. We generate them at build time. We generate Spring data repositories, and this is all behind one flag. But if you want to opt in one and not in the other, we have to do it more modular, so there are more properties to choose from. We could pre-compute the class path scanning. So if Spring Framework starts up, it usually tries to find all your bean methods and all your add components and add configuration classes. We could pre-compute that and store that somehow. We want to fix the condition evaluation so that, for example, add profile maybe works in when you're using Spring AOT. Would be great. And also other hook points for our Spring portfolio projects, or for your Spring Boot starters to hook into this optimization thingy, so that you can, for example, generate code and stuff like that. This is the current prototype, but it's really a prototype, so you can essentially opt into the stuff you want to have. For example, in this case, we don't want to freeze the bean registration, but we want to predefine classes. We want to create a class path index, but we don't want, this is GraalVM reachability metadata, which is essentially telling GraalVM where reflection is happening, and other dynamic features. Okay, so there is more to come. Okay, actionable right now. Using Java 25, AOT cache, and Spring AOT, no prototype JDKs, no preview flags, no Leyden self-compiled stuff, just Java 25 GA. It improves your startup time by 4x if you're using AOT cache, even when just doing the poor man's training run, which you can easily do on your CI system. It decreases the CPU consumption during startup and warm-up by a factor of 2.6x, and this only will improve in the future JDKs. So you can do that right now if you want to get some free startup speed, which is like a really cool feature. And with that, thank you very much. And I have some time for questions. Yes, please. The question, if I got that right, is are there any limitations? I guess we are talking about the poor man's training run. There are no limitations, no. It depends if you wired your lifecycle stuff correctly. So if your application is essentially doing something in here, then it will be invoked and your code will crash. But if you implement the lifecycle method, the start method, then it won't be executed and your code won't crash. So this is the trade-off here. But besides that, it starts up your application to a certain point and then it just stops. There are the trade-offs here is with Spring AOT. Spring AOT has trade-offs, like real trade-offs, that it freezes the bean arrangement, but the poor man's training run does not. You can just use it. Yes. So the question is, hold the numbers up in production. The problem is, I only write frameworks and not production apps. So it's like the problem with benchmarks is benchmarking is like really, really hard. And it works with Spring Pet Clinic, and Spring Pet Clinic is a production-like application. So it's not a Hello World endpoint, which just returns Hello World in JSON or some other silly example. But this thing has like time leaf templates, it had a web layer, it has a database, it had Hibernate in it. So there's a lot of enterprise components already in it. And here you can see it holds up. But if it holds up for your application, I have no idea. I'd guess you just have to test it. I mean, if the class loading and stuff is your problem in startup, then it will fix that. But if you spend like 1 minute repopulating caches and stuff, this doesn't fix the problem. So it heavily depends on what the application is doing in startup. Does this answer your question? Okay. Cool. Then I guess it's beer time. Thank you.